Okay, so this afternoon, we want to look at how to solve systems of linear equations. So basically, you have got equations where the unknowns are raised to the power 1, systems of linear equations, and our main focus is a special kind of system of linear equation which is known as the triangular linear system, which is what you're going to see very soon. Okay. So in this particular case, now a triangular linear system is an important step. Obtaining a triangular linear system is an important step to solving systems of linear equations. And of course, there are two types of this triangular linear system which we're going to look at. There is what is referred to as an upper triangular linear system. There is also what's referred to as a lower triangular linear system. The upper triangular linear systems, these are worked out using what's called back substitution. In the lower triangular system, these are worked out using what's known as forward substitution. So for a upper triangular system, it usually has this kind of form. So for example, we have this equation which we have here: 4x1 minus x2 plus 2x3 plus 3x4 equals to 20, minus 2x2 plus 7x3 minus 4x4 equals to minus 7, 6x3 plus 5x4 equals to 4, 3x4 equals to 6. So with what you can see here, of course, there is these numbers, the 4, the 2, the 3, these are what are called coefficients. And then there is this one, the x1, x2, x3, x4. These are what we refer to as the unknowns. Then anything after the equal sign, those are just basically the constants. Okay, now with what you're seeing here, each of these unknowns, x1, x2, x3, x4, in all these equations you can see each of them is only raised to the power 1. That's why these are linear. Otherwise, if any of these unknowns were raised to the power 2, then it would assume a quadratic form or a cubic form or a polynomial, a non-linear polynomial, basically, as you have seen with the equations we were working out in the last chapter, where we're looking at solutions to non-linear equations. So anything which is not raised, whose highest power has not been raised up beyond 1, then that is what is referred to as a linear system. Now, when you're trying to work out systems of linear equation, like in this case, you have got x1, x2, x3, x4. So basically what we have here, as you can see, we have got 4 unknowns. Are we clear?
Yes, sir.
We have got 4 unknowns. Now, mathematics rules demand that if you have got 4 unknowns like these, x1, x2, x3, x4, you need to have 4 equations for you to be able to work out this system of linear equations. So if you have got 4 unknowns, you need 4 equations. If you've got 5 unknowns, you need 5 equations. If you've got 10 unknowns in an equation, you need 10 equations for you to find unique solutions to each of those unknowns. Okay, so in our case, we have got 4 unknowns and we have got 4 equations like this. And the equations which we have got this form. You can see where it looks like it's a triangle like this. And it will become very apparent why it looks like this, because it actually does form when you put this kind of equation in another format, which we're going to see how we're going to do that. It actually does look like an upper triangular system. So if you've got your equations, a linear system like this, then it's arranged in this manner. The equations are arranged in this manner. This is what is referred to as an upper triangular linear system. Are we clear? Anything which looks like this is what is referred to as an upper triangular linear system. Are we clear?
We are clear, sir.
Yeah. The other thing is, you have to be aware of, we're doing mathematics, and this mathematics has to be done with computers. But at the same time, we are not going to go too much into the detail like where people study mathematics. We need to use mathematics, yes, because people study physics, but we need to have a good understanding of what it is we're doing, because this mathematics which you're trying to do eventually has to be transferred into something which a computer is going to understand. Okay, now when you have a system like this, an upper triangular linear system, you start with the last equation, the fourth equation. This one, 3 x4 equals to 6. Using this last equation, you work out for x4. So when you do that, for 3 x4 equals to 6, in that case, your x4 is going to be equals to 6 divided by 3. So you divide by 3 this side, you divide by 3, so you end up with x4 equals to 6 divided by 3, and that's going to give you, that's going to give you x4 being equals to 2. Once you get your 2, you are going to use the value of 2 you have obtained here in the second last equation. So once you find your x4, which is equals to 2, you're going to use it here. As you use it here, you want to use that to find x3. So in that case, you're going to have your this bit, 6x3 will be equals to 4 minus 5x4. Then you divide both sides by 6. You're going to end up with x3 equals to 4 minus 5x4 divided by 6. Then you work out what x3 is. So you start with the bottom here. Then the values you're going to find, you substitute them back in the equation which is up above the equation you've worked out. So when we do this, we're going to find x3 and x4. Values of x3 and x4, we're going to substitute them here where there's x4 and x3 so that we can find x2. Then once we find x2, our values of x2, x3 and x4, we'll substitute them here, here and there so that we can find x1. This process where you have your equations, your linear equations arranged in this manner, then you start with the last equation, you find what the value of the unknown is, then you use that value of unknown, you substitute it up, then you keep on going until you find all of them. This process is what is referred to as back substitution. Are we clear?
Yes, sir.
So when you have an upper triangular linear system, upper triangular linear systems, whenever you have them, you solve them using back substitution, and that's what you're going to do. So in this particular case, so we have our x4 equals to 6 over 3 and our x4 that's equals to 2 here equals to 2. Then our x3 is going to be 4 minus 5, so it's 4 minus 5 x4 divided by this bit here, the coefficient which was in front of the x3, which is a 6, like that. Our x4 is 2, so you put the 2 there, so you end up with x3 equals to 4 minus 5 times 2, then divided by 6, you end up with x3 equals to minus 1. So now we have found a value for x4, which is equals to x4 equals to 2. You found a value for x3, which is equals to minus 1. Now that we have got values for, now that we know how much x3 is minus 1 and x4 is equals to 2, we can use these values in the second equation to find what's going to be our value for x2. So if you look at the second equation, which we have, our second equation is this one. This is our second equation. So for this second equation, if we get these guys to the other side, so you're going to have minus 2x2 equals to minus 7 minus 7x3 plus 4x4. Then if you divide by minus 2 on both sides, you're going to end up with minus 2. You're going to end up with x2 equals to minus 7 minus 7x3 plus 4x4 divided by minus 2, which is what you have here. So your x2 is equals to minus 7, then your x3 is what we put here, minus 1, then plus 4, then your x2 is what we put here as a 2, then this whole thing you divide it by minus 2, then you're going to end up with x2 is equals to minus 4. Is it clear? Now we have x2 is equals to 2, x3 is equals to minus 1, and x2 equals to minus 4. So with these values of x2, x3, and x4, we're going to use these values in the first equation. This one, 4x1 minus 2 minus x2 plus 2x3 plus 3x4 equals to 20. So we transfer all these guys to the other side. So we're going to end up with 4x1 equals to 20 plus x2 minus 2x3 plus 3x4. Then the whole thing divided by 4. So we're going to end up with x1 is equals to 20 plus x2 minus 2x3 minus 3x4, the whole thing divided by 4. Then we substitute the values of x2, x1, and x3, which we have obtained. And when you do that, we're going to end up with the following. We're going to end up with this. We're going to end up with x4 being equal to 20 plus minus 4 minus 2 x1, minus 2 minus 1 minus 3, then 2, then you put your thing there, you're going to end up with x4 equals to 3. So that's how equals to, x4 equals to 3. So this is how you would work out a triangular linear system. It doesn't matter whether this system has got 4 unknowns, this system has got 5 unknowns, it doesn't really matter. Here, as you can see, we have created a generic system of linear equations. In this system of linear equations, we have got 6 linear equations, and in these 6 linear equations, we have got 6 unknowns. So the number of unknowns, if you've got 6 unknowns, you need to have 6 linear equations. The first one is this one, a11 x1 plus a12 x2 plus a13 x3 plus a14 x4 plus a15 x5 plus a16 x6 equals to b1. Then this other one here, a22 x2 plus a23 x3 plus a24 x4 plus a25 x5 plus a26 x6 equals to b2. Then a33 x3 plus a34 x4 plus a35 x5 plus a36 x6 equals to b3. Then a44 x4 plus a45 x5 plus a46 x6 plus equals to b4. Then a55 x5 plus a56 x6 equals to b5. a66 x6 plus b6 equals to b6. One of the things you notice which we are doing, which I have done without explaining anything to you, is how I have written the coefficients, the a. I've not just written a, I've written it as a11. Now the reason why I've done this like this, why it's written like this, is because it turns out, as I'm going to show later on, that it's possible for you to actually write your system of linear equations in terms of matrices, so that these coefficients in front of the unknowns, our unknowns are x1, x2, x3, x4, x5, x6. The coefficients, these a coefficients in front of our unknowns, x1, x2, x3, x4, x5, these coefficients are going to be put in a matrix. And if we're going to put them in a matrix, then these coefficients are going to be elements of a matrix, and for each element of a matrix, we need to refer to the element of a matrix using a row. So the first digit refers to a row, the second digit refers to a column. So matrix elements, you refer to them using a row and columns. So this first coefficient is going to be an element which is going to occupy row number 1, column number 1. This one is going to be the element which is going to occupy row number 2, row number 1, column 2. This one is going to occupy row number 1, column 3. This one is going to occupy row number 1, column 4. This one is going to occupy row number 1, column 5. This one is going to occupy row number 1, column 6. That's why we have written these things like this. Are we clear? Is it clear why these things are being written like this? Because we're going to put them in a matrix, and these coefficients are what are going to be the matrix elements. And for each matrix element, you need to know what is the row which this particular coefficient is going to have, and at what column is it going to be on. Okay, but that's for later. For now, what we are saying is, it doesn't matter whether you've got 4 unknowns or 5 unknowns. In this particular case, we have got 6 unknowns. If you've got 6 unknowns and you're talking about a linear system, then you need 6 linear equations. And for a triangular linear system, this is how it's going to look. As long as you've got a triangular linear system like this, which we have called, we have said this is an upper triangular linear system, then you can solve this triangular linear system using back substitution. So you're going to start with the last equation. With this last equation, which is this one, a66 x6 equals to b6, you're going to work out x6. So in that case, x6 is going to be your b6 divided by a66. Are we clear? So you start from the bottom, then you start going up. The value of x6, which you have found, that's what you're going to use here. Then when you use it here, you are going to work out x5. So when you're working out x5, this bit, you take it to the other side. So you're going to have b5 minus f minus a56 x6, then the whole thing divided by a55. So you're going to end up having x5 being equals to b5 minus a56 x6 divided by a55. That's how you're going to get your x5. So you have your x6, then you have your x5. Now, next you're going to use your x6 and x5 values to find x4. So in finding x4, you're going to use this equation. So you already know what x6 is. You have found what x5 is. So these terms, we'll transfer them to this side. So you're going to have b4 minus a45 x5 minus a46 x6. Then the whole thing is going to be divided by a44. So you're going to end up with x4 having the following form. You're going to have x4 being equals to b4 minus a45 x5 minus a46 x6 divided by a44. Is it clear what you're doing?
Yes, it's clear. Yeah, following.
We are assuming that somehow you have managed, you had some equations, then you have managed to manipulate your equations so that they look like this. You at this stage, you have already, how you did this at this particular moment, we don't know, but you have done it. You are at this particular stage. If you are at this particular stage, then we are trying to show you how you are going to work out things. Okay, so we move on to how, after we have found our x4, then how we're going to find our x3. So for us to find our x3, we'll get all these terms to the other side. So you're going to have b3 minus a34 x4 minus a35 x5 minus a36 x6. The whole thing divided by a33. So in that case, your b3, your x3 is going to be b3 minus a34 x4 minus a35 x5 minus a36 x6 divided by a33. So you find your unknown x3. So by this stage, you would have known what your x3 is, what your x4 is, what your x5 is, what your x6 is, and you would use this information to work out try to find out what your x2 is supposed to be. So when you try to find out what x2 is supposed to be, all these terms here, you transfer them to the other side. So you're going to have b2 minus a23 x3 minus a24 x4 minus a25 x5 minus a26 x6, then the whole thing divided by a22. So you end up with your x2 being equals to the following. So you end up having x2 being equals to b2 minus a32 x3 minus a24 x4 minus a25 x5 minus a26 x6 divided by a22, like this. Okay, then at this particular point, we have almost everything we need. The only thing now we need to do after we find our x2, now we need to use the first equation for us to find x1. So here, so we get all these guys to the other side. When you get all these guys to the other side, so you end up having b1 minus a12 x2 plus a13 x3 plus a14 x4 plus a15 x5 plus a16 x6 divided by a11. So when you do that, you end up having this. X1 is equals to b1 minus a12 x3 minus a14 x4 minus a15 x5 a14 x4 minus a15 x5 minus a16 x6 divided by a11. Are we clear? Now, The other thing I want you to bring to your attention is the following. You'll notice, apart from this one, apart from the first one you work out, which seems to be a bit different, apart from the first one you work out, this, the first thing you notice is the following. If you are working out the first one, x6, you work out x6, then your b is going to have a 6. Is that clear? If you work out x6, when you start with x6, your b is supposed to have a 6, and this a is supposed to have 6 and a 6. Can you see that? Hello?
Yes,
We need to start seeing certain things. If this first one here, whatever it is, x6, the b has got a 6, the a has got 2 6 and 6 6. That is how all the time the first answer you're going to be getting will have this form. x6, whether it's x10 is going to be equals to b10 divided by a10 10, or x8 is going to be b8 divided by a8 8. That's the first one. The first answer you work out using back substitution will have this form. After that, what comes next? Your x5. For x5, in this particular case, you notice the following. Your b has got a 5. Your a's have got 5 5. Then next comes this coefficient. The next coefficient which comes, the a. The a coefficient will have the same number as this one, the 5. So basically, the same 5 which you have here, that's a 5 which you have here, that's a 5 which you have here. The other one, the column one is going to be increased by 1. So it's 6, or whatever column value you have here, it's going to be increased by 1. It will be 6, and that's what the x value has. So the x value is going to be 6, and the column value is going to be 6. So they'll be increasing in this fashion. So if there was something else here, you're going to have a5, then, so this side you're going to have minus, you'd have minus, if there was something, you'd have minus a5, then 7x7, then you've got minus a5, 8x8, like that. Are we clear? The next solution we are supposed to find is x4. So x4 will start with a b4 minus a44. x4 will start with a b4 minus a44 divided by a44 at the bottom here. Then you have a minus. Then the value of a, the row column, will be the same as the x value, which is going to be, so you're going to start with the b4, then you're going to have a4, then after a4 you start with the column value is going to be 5. Then this one is going to be x5. So you're going to start with x4 is going to be b4 minus a 45 x5 minus a 46 x6 divided by a44. And that's exactly what you notice. There are things which need to be noticed about what's happening. x4 is equals to b4 minus a, this number here, this 4 is for the number of the column, so the number of the row, which is what is going to have here, all of them, your coefficients, because your coefficients, all of them came from the same row, so they're going to have a 4, they're going to have a 4. Okay, then after that you have your column. your thing will increase by 1. So here you're going to have 5, then you're going to have x5, then minus a46, x6, like that, up to whatever number of coefficients, whatever number of unknowns you have. Here, for x3, it's going to start with b3. The whole thing is going to be divided by a33. If it starts with b3, the coefficients minus a will have 3's. All the coefficients, the Coulomb law will be 3. There will be 3. But when it comes to the the rows will be 3's, but when it comes to the columns, it will increase by 1. So instead of having a 3 here, it will go to 4. So column number 4, then x4 minus a3, 5, x5 minus a3, 6, x6, like that, until you get to the required number of unknowns. Is it clear what's going on?
Yes, sir.
The same thing is happening here. B2. So it will start with B2 here. Then at the bottom here, you got A22, but minus the next term which is going to come, will have A. Right? The row is going to be the same as this B. So you're going to have a 2. But then the column will increase by 1. So you're going to have 3, x3, then you're going to have minus 4 minus A, 4, 2, x4 minus A, 2, 5, x5 minus A, 2, 6, x6, like that. You can't go beyond this, go to 7, because you only have 6 unknowns. So you can only go up to a certain number of unknowns, which is something you already know ahead of time. The same thing is happening here. We always, x1 equals to b1, then at the bottom here, there's a11, then you're going to start with minus the coefficient a. For the coefficient a, the row of the coefficient is the same as the row number for this, which is just 1. So you're going to have 1 here, you're going to have a 1 here, you're going to have a 1 there, you're going to have a 1 here, you're going to have a 1 there. Then after that, the column will increase by 1. So you have a 2 here, x2, 3 here, x3, 4 there, x3, 5 there, x5, 6 there, x6. So that is something to notice in this. It's not just that the numbers found themselves there. No, there is a pattern in how this thing is being done. Are we clear?
Yes, sir.
Okay. So that's something which we need to notice. Now, why did we write things the way we wrote them like this, with numbers, with our coefficients showing, oh, this one is supposed to be coefficient, this column, then this row and column? Like, why did we do that? Now, if, for example, we just consider the most general case, where you have, like, what you're going to have normally be given an equation like this: a11 x1 plus a12 x2 plus a13 x3 plus a14 x4 plus a15 x5 plus a16 x6 equals to b1. And in this equation, the unknowns are x1, x2, x3, x4, x5, x6. So we've got 6 unknowns. N is equals to 6 unknowns. Then the coefficients are what you have here: a11, a12, a13, a14, a15, a16. Then of course there's this bit here, which is your b, which is a constant b1. Now if you have 6 unknowns, for you to find unique values for x1, x2, x3, x4, x5, x6, you need to have 6 other equations of the same type. And that's why we have got these. These are the equations. So you've got 1, you've got 2, you've got 3, you've got 4, you've got 5, you've got 6. You need 6 other equations like these. Now, when you do this, it's possible for you to do the following. You can rewrite all this information in a much more compact way. You can move from this, writing like this, you can move to this, where you write your system of linear equations in the form of a matrix product, where you've got A, matrix A, multiplied by X equals to B. Now in this case, matrix A is going to be the matrix of coefficients, these A coefficients, A11, A12. So all these coefficients with their row and columns we will just get all the coefficients, we'll put them together in one matrix. Are we clear? So that's what matrix matrix A is going to be. Matrix A is going to be our matrix of coefficients. Then matrix X is going to be a column matrix of these unknowns: x1, x2, x3, x4, x5, x6. So all these 6 unknowns, we're going to put them in a column matrix. Then we come to B here. B is going to be also a column matrix of these constants which you have here: B1, B2, B3, B4, B5, B6. So all the information which you have, all this information we can put in the form of a matrix and rewrite in this form: AX is equals to B. Now when we do that, when we put all our coefficients in a matrix, this is what we're going to have. Our matrix A is going to look like this. You're going to have A11, A12, A13, A14, A15, A16. A21, A22, A23, A24, A25, A26. A31, A32, A33, A34, A35, A36. A41, A42, A43, A44, A45, A46. A51, A52, A53, A54, A55, A56. A61, A62, A63, A64, A65, A66. So these are all the coefficients. We have collected all of them. These coefficients here, we have collected all of them. All the coefficients on the left hand side of the equal signs, we collect all of them, and depending on their things, we put them in this. So this is what is referred to as a coefficient matrix. This is what we call a coefficient matrix. Are we clear?
Yes, sir.
So this is part of the information which we have about this system of equations, a coefficient matrix of A. The other one is the X. The X is going to be a column matrix of the unknowns. So our X is going to be the following. Our X is going to be this. Matrix X is going to be a column matrix of x1, x2, x3, x4, x5, x6. And so these are unknowns. And the other ones, the constants on the right hand side of the equation, that's what you're calling B. That's going to be a column matrix of B1, B2, B3, B4, B5, B6. With this arrangement, we can rewrite, we can present our information like this. So you're going to present our information like this, where this bit here is the coefficient matrix A, this bit here is the column matrix of the unknowns, and this bit here is the column matrix of the constants. Are we clear?
Yes, sir.
Now we are going to show that when we do this, this is the same as what we had before. When you arrange information like this, as AX equals to B, this is the same as what we had before. This, we want to show that this which you have here, like this, and what we have here, these are equivalent. They look different, but they're the same. Okay, so how do we do that? Of course, here, this is matrix A, this is matrix B, this is matrix A, this is matrix X. So we can do multiplication. When you're multiplying matrices, you multiply the row. So you multiply the row by the column, right? So you do row, you get the first row, you multiply it by the column of this guy. So when you do that, when you do the multiplication, so this A11 is going to multiply the X1, so you're going to get this. The A12 will multiply this bit, you're going to get this. Your A13 will multiply the X3, you're going to get this. The A14, you multiply your X4, you're going to get this. Your A15, you multiply your X5, you're going to get this. Your A16 will multiply your X6, you're going to get this. So when you're doing column things, you multiply the row by the columns, then you add. So you're going to end up with this. You do the same thing here. The second row multiplied by the column, you're going to end up with this. You do the same thing here. You multiply third row by the column, you're going to end up with this here. You get your fourth row, get your fourth row by the column, you're going to end up with that. Do the same thing for the fifth row. Get a fifth row, you multiply by this column, you're going to end up with this. You multiply your sixth row by the column thing, you're going to end up with this. So basically what we are saying is whatever we have this side, all this is equal to this bit here. So the rows, we're saying the rows are equal. If the rows are equal, then you can just equate this thing here, this first row to the first row here, which is what's going to give you this A11, X1, like that. Then this second row here of this matrix, you equate it to this second row here, you get yourself this bit here. Then this third row, you equate it to this guy here, you get yourself this thing here. And this fourth row, you equate it to this guy here, you get yourself this one here. Then this fifth row, you equate it to this guy here, you get yourself this one here. Then this sixth row, you equate it to this row, you get yourself that bit. So you see that at the end of the day, we have recovered what we had. Is it clear that we have come back with what we started with? We changed our system of six linear equations with 6 unknowns. We changed into a matrix product of AX equals to B. That matrix product of AX equals to B is the same as what we had before. They're equivalent. They're not the same, but they're equivalent. Basically, we say that they're equivalent since they don't look exactly the same. Is that clear?
Yes, it's clear.
Any questions? So we need this idea to say, when you have a system of linear equations, this system of linear equations can be written as a product of coefficients times a matrix of coefficients times a column matrix of unknowns equals to a column, a column matrix of the constants, the B's. Are we clear?
Yes, sir.
Okay, so now that we know that we can do this, which is possible, and our interest is in these guys called triangular linear systems, the upper triangular linear system, which is what we have been looking at. So we're going to go back to our upper triangular linear system, which is what we have here, a triangular linear system of 6 equations with 6 unknowns, which is our A11 x1 plus A12 x2 plus A13 x3 plus A14 x4 plus A15 x5 plus A16 x6, like this, the way it is here. Now, you notice that, yes, it looks triangular like this. The reason why it looks triangular like this is because the coefficients, like the one which is supposed to be here, the A21 coefficient, the A21 coefficient is 0. So 0 times x1 is just 0. That's why there is nothing here. So where it looks like there's a space here, it's because the coefficient which is supposed to be there is 0. You come here, you've got your A31 x1, but the coefficient A31 is equal to 0. You come here, A32 x2, but the coefficient A32 is equal to 0. The same thing happens here with your 4. You've got A41, you've got A42, A43, all those coefficients are 0. So you multiply 0 times whatever your unknown is, you just get 0. The same thing is happening here. You have got your A51, these guys, these. So in this particular case here, in the second line, this coefficient, A21, this is 0. That's why there's nothing here. So 0 times x1 is just 0. In this third line here, this coefficient here, A31 is equal to 0, A32 is equal to 0. So when you do that, you start ending up with this. Then here, if you make your F01 equals to 0, you make your F02 equals to 0, you make your F03 equals to 0, then you end up with this. If you make your F51 equals to 0, if you make your F52 equals to 0, if you make your F53 equals to 0, then your F56 equals to, F54 equals to 0, then you end up with this. If you make your A, what's this? If you make your A61, A62, A63, A64, A65 equals to 0, then you end up with this. Are you clear?
Yes, sir.
So, what you should notice if you go look carefully at what's happening, we compare here. We know the 2 is the one which is giving us the column, sorry, the row, and the column is the 1. If you compare the 2 and the 1, the row is 2, the column is 1. This one is becomes 0. So whenever, for you to create an upper triangular system, you need to make sure that the column values, the row values of your coefficients are greater than the column values. And for each coefficient, basically what I'm trying to say is that for each coefficient where the row value is greater than the column value, you make that coefficient 0. Like here, you've got a 2. The 2 is for the row, 1 is for the column. So you can see the row is the row is greater than the column. So you make this one a 0. This coefficient is 0. You come to this other one, 3, 1. The row is 3, the column is 1. So the row is greater than the column. So you make this coefficient equals to 0. You come and inspect this one here. 3, 2. The row is 3, the column is 2. So the row is greater than the column, so you make this one equals to 0. You come here, this is 3, 3. The row is 3, the column is 3. So the row is not greater than the column, so you leave it. So everywhere where the row is not greater than the column, you leave it. But everywhere the row is greater than the column, you make that coefficient become a 0. Here, F1, the row is 4, the column is 1, you make this a 0. F42, the row is 4, the column is 2, so 4 is greater than 2, you make this a 0. You come here, F43, the row is 4, the column is 3, so 4 is greater than 3, you make this a 0. You come here, F44, the row is 4, the column is 4, so 4 is not greater than 4, you leave it. You come here, F51, the row is 5, the column is 1, so 5 is greater than 1, you make that a 0. F52, the row is 5, the column is 2, so the row is greater than the column, so you make this a 0. F53, okay, the row is 5, the column is 3, so 5 is greater than 3, so you make this become a 0. A54, the row is 5, the column is 4, so 5 is greater than 4, so you make this coefficient become a 0. F55, the row is 5, the column is 5, 5 is not greater than 4, so you leave it. You come here, A61, the row is 6, the column is 1, so 6 is greater than 1, you make this a 0. A62, the row is 6, the column is 2, so 6 is greater than 2, so you make this coefficient become a 0. A63, the row is 6, the column is 3, so you make this coefficient, 6 is greater than 3, so you make this coefficient become a 0. A64, in this particular case, the row is 6, the column is 4, so 6 is greater than 4, so you make this guy become a 0. A65, the row is 6, the column is 5, so 6 is greater than 5, so this guy becomes a 0. A66, the row is 6, the column is 6, 6 is not greater than 6, so you leave it. So at the end of the day, you notice that you will manage to come up with this by making certain coefficients become 0. Are we clear?
Yes, sir.
Yes, sir.
Is it clear to everyone? What criteria we are using to come up with this? It's by making sure that we go for each coefficient where the row the row number is greater than the column number. For all those coefficients where the row number is greater than the column number, we make those coefficients become equals to 0. So when you do that, this is what you're going to end up with. We can rewrite this by explicitly by indicating where our zeros are. When we explicitly indicate where our zeros are, like here, this one we made 0, this one we made 0, this one we made 0 here, this one was made 0, this one was made 0, this one was made 0, this one was made 0 here, this one was made 0, this one was made 0, this one was made 0 here, then here we made 0, this one is made 0, this one is made 0, this one is made 0, this one was made 0. We can rewrite all these. If we explicitly show where the zeros are and the unknowns and everything like that, we can rewrite our upper triangular system in this fashion. The reason why we are doing this is so that we can rewrite our triangular system as a product of AX equals to B, where A is the matrix of coefficients, B is the column matrix of the unknowns, and sorry, X is the column matrix of the unknowns, and B is the column matrix of the constants. Is this clear?
Yes.
So when you do that, our A is going to have the following form. Our matrix A is going to have this form. Our matrix A will have this form. This is going to be our A matrix. Then our X matrix is going to be this. Then our B is going to be this. So where A is this. This is where the name upper triangular comes from. You can see the coefficients which are not equals to 0, the ones which are above the diagonal here, these coefficients which are not equals to 0, they form a very nice triangle. Then your X is your x1, x2, x3, x4, x5, x6. Then your B is your b1, b2, b3, b4, b5, b6. You can do that. Is it clear?
Yes, sir.
Okay. Next, from this, when you multiply this row times this column, 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 we expect you to get back what we had, what you started with. Okay. So, generally, when you are trying to define what is, how do you form an upper triangular matrix? So if you have got a matrix which has got the same number of columns, the same number of rows and columns, like in this case you've got matrix A with whatever the coefficients are in that matrix. The coefficients are A, IJ, where I is the number, the row, so I is the row and J is the column. Your matrix A with this Aij is going to be called an upper triangular matrix. It's going to be an upper triangular matrix if you make sure that for every I which is greater than J, for every coefficient with I greater than J, you set that coefficient to being equal to 0. For every coefficient Aij where I is greater than J, where the row number is greater than the column number, if you set all those coefficients where such a condition is met, where the row number is greater than the column number, you set them to 0, then your matrix A, which is a square matrix, it needs to have the same number of rows and columns. Then that square matrix, if you impose this condition, then it's going to transform, it's going to become what is called an upper triangular matrix. On the other hand, if you impose a condition to say for your matrix A, you want to make sure that for every coefficient Aij, where the row is less than, the row number is less than the column number. If the row number is less than the column number, you want to make sure that that coefficient becomes equals to 0. Then what you're going to end up with is something called a lower triangular matrix. Are we clear? So this kind of an arrangement where you have your upper triangular matrix, then you write it like this: Ax equals to B. This is what's basically what is called an upper triangular system. And generally, if you have got n linear systems with n unknowns, then you can express your stuff as a triangular system like this, like what you have here. Depends on whatever number of n you have. We have looked at 6. We started with 4. We looked at 6. You can go as far as you want. Okay. Now, for this whole thing to work, if you have an upper triangular system, fine, you can have an upper triangular system. However, for you to do back substitution, for back substitution to be done, you need to make sure that the coefficients, those elements in your matrix, in your upper triangle, in your matrix system, where the row number is equal to the column number, these guys, A11, A12, A33, these guys, you need to make sure that these guys, AKK, cannot be equals to 0. If any of these diagonal elements, these ones, A11, A22, A33, A34, A35, A36, if any of these diagonal elements are equals to 0, then you will not be able to do your back substitution. Are we clear?
Yes, sir.
Remember, for everything, when we're doing x6, we divided by a66. When you're doing x5, you divided by a55. When you're doing x4, you divided by a44. When you're doing x3, you divide by a33. When you're doing x2, you divided by a22. When you're doing x1, you divided by a22. So if any of them is equals to 0, you can't do a division by 0. So it's not going to work. So for back substitution to happen, for you to be able to carry out back substitution, you have to make sure that all these guys, A11, A22, A23, A24, A25, A26, all these guys, none of them is equals to 0. Are we clear?
Yes, sir.
So assuming you have a triangular system, then you decide to write your triangular system in this fashion, like this. You have a triangular system, then you write your triangular system as a matrix of A, X equals to B. Then, if all your diagonal elements, the elements whose row number is equal to the column number, if these diagonal elements are not equal to 0, then it tells you that it's possible for you to find a solution. Then there exists a unique solution to your linear system, and this solution you can find using back substitution. However, if any of them is equals to 0, then it will not be possible for you to find a unique solution. So if that's the case, then the solution is easy to find. Then you can always start with the last equation, like I said. So you start with xn, that's going to be bn divided by a and n. Right? Are we clear?
Yes, sir.
Then, if you come with this one, x. Now, remember what we did. Next one, x, n minus 1. N minus 1 is the number of the row. So, your b is going to be b, then it's going to have the same number, the same row, b n minus 1. So your b is going to have the same number as this one. So you're going to have your n minus 1. Then your a is going to be a, n minus 1, n minus 1. Are we clear? Remember what we did when you're looking
Yes, sir.
at the relationships of how the row and the other things change, then you're going to have a minus, then you're going to have an A. This A, the row is going to be the same as all the other things. So it's going to be n minus 1. However, when it comes to the column, you need to add 1. So your n minus 1 plus 1, n minus 1 plus 1 is going to give you n, and you're going to end up with x n. So your x n minus 1 is going to be b n minus 1 minus a n minus 1 n x n divided by a n minus 1 n minus 1. Similarly, here, your x n minus 2, your x n minus 2, so you're going to have your b, this n minus 2 is the row number, so you're going to have your b, n minus 2 here. At the bottom, you're going to have your a, n minus 2, n minus 2, then next you're going to have a minus, then you're going to have the a, but the a is going to have the same row number as this, so you're going to have a, n minus 2, then next you're going to have the column. The column number is going to be 1 plus n minus 2 plus 1. That's going to, so n minus 2 plus 1 is just going to give you n minus 1, then x n minus 1, then another minus a n minus 2, then you add 1 to what you have. So you're going to end up with n, then you're going to have xn here. So when you do this process, basically we would need it, but what we're trying to say here is you're going to have the following. Okay, when you start with, after you've worked out these, xn, the last one, xn is equals to bn over an. The other things you're going to work out, they'll start as follows. And I want people to follow this properly. They'll start as follows. 1, you start with xk. So when you start with xk, your b, so the k here is the row number. Okay, the k is the row number. We have already worked out the last one, the last row, which is the n. xn is equals to bn over ann. Then after you work out the last row, the other things you are left with, the second last one is n minus 1, followed by n minus 2, followed by n minus 3, followed by n minus 4, like that, until you get back to 1. So our k's, our row numbers, will start from n minus 1, because for row number n, we have already found what xn is. It's here. So the next thing we're finding is for n minus 1. After we find n minus 1, we're going to find for n minus 2. After we find for n minus 3, we're going to find for n minus 3. After we find n minus 3, we're going to find for n minus 4, n minus 5, until we end up with 1. So we are going to be going backwards. Are we clear?
Yes, sir.
Now, how do we go backwards? By tracking what row we are at. So you start with this one here. So xk. So your b is going to have the same k, because the row number has to be the same. So xk, bk. First thing, which is very cheap, is at the bottom. You're going to have a kk, right? Is that clear? You're going to have AKK. The other thing, then we're doing minus everywhere here. There's minus everywhere. There's minus, 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 minus. So we're going to put a minus here. So we're going to be doing minus. But as we are doing minus, we need to track the A's. So as you can see, this one, n minus 2, n minus 2. This n minus 2 is the number for the row. So this k which you have here, which is the row number, is the same k you're going to have is the same row number you're going to have for the A. So the same k you have here is the same k you're going to have here. However, when it comes to the j, for us to get j, we need to add 1 to this. We need to keep on adding 1, 1, 1, 1, 1. So we add 1, we add 2, we add 3, we add 4, we add 5. We need to keep on adding to the row number. So our j, which is going to be the row number, is going to be k plus 1. So every time for a particular j, we'll keep on adding like that. So you end up with a kj xj. The j which you have here, which is what you have here, is the same as the j which you're going to have, the column value which you're going to have for the unknown, like this. So that's how this expression basically comes about. It's taking advantage of what we have noticed here. Are we clear? This is very important because this is what we're going to use. This is what computer programs which try to solve back substitution do. They try to use this expression repeatedly. They will first do this, then after doing that bit here, after doing this bit here, then we'll start doing this. They would start doing this, running through this repeatedly, as you can see, and until we get what we want. Are we clear?
Yes, sir.
Okay. So, what? Yeah. The other thing which is important is if you have got the matrix, matrix A, then your matrix A is a n by n matrix, which is either an upper triangular matrix or a lower triangular matrix. There is a quantity you can work out which will help you find out if you can find answers to this particular thing. And that quantity is what is referred to as the determinant. Now, this is the determinant of an upper triangular matrix or a lower triangular matrix. That's what we're talking about here. You can only use this expression for a determinant of an upper triangular matrix or a lower triangular matrix. So we're saying the determinant of A, which is an n by n matrix A, which turns out to be an upper triangular matrix or lower triangular matrix, can be found by multiplying these guys. The diagonal elements, A11 multiplied by A1 by A22 multiplied by A33 multiplied by ANN. Basically, this is how you write a product of the diagonal elements from I equals to 1 to n. So when you multiply these diagonal elements, and it turns out that when you multiply these diagonal elements of your upper triangular matrix or lower triangular matrix, the product is what's going to give you the determinant. If the determinant is not equals to 0, then it's telling you that a solution exists. Otherwise, if your determinant is equals to 0, because one of these guys or more of these guys are equals to 0, then it tells you that there is no unique solution. Is that clear?
Yes, sir.
So for you to do back substitution, once you have your upper triangular system, then you have written your system in the form of ax equals to b, like this. The first thing you need to do, you need to work out the determinant of A, which is the upper triangular or lower triangular matrix. You work out the determinant. If the determinant, by multiplying the diagonal elements, which is what you're doing here, you work out the determinant by multiplying the diagonal elements. If you multiply the diagonal elements, then their product is not equals to 0, which means the determinant is not equals to 0, then it means that there is a solution. Then after you confirm that, okay, fine, a solution is there, then the next thing you're going to do is you're going to go to the last equation. Then you're going to do this. You're going to work out this. Xn is going to be equals to Bn over Nn. Once you do this, then now you can do this. You can work out the rest of the values using this expression. Xk is equals to Bk minus the summation of j equals to k plus 1 equals to n akj xj divided by akk for k equals to n minus 1, n minus 2, n minus 3, all the way back up to 1. So that's how back substitution works with an upper triangular system. Are we clear?
Yes, sir.
So today we stop here. We have looked at an upper triangular system and how do you carry out back substitution. Tomorrow we're going to look at a lower triangular system and how do you do forward substitution. So for an upper triangular system, you do back substitution. For a lower triangular system, you do forward substitution. All these are things which we need to know so that we can move on to the next step of, once you're given some particular system, how do we manipulate that system so that it becomes a triangular system. Are there any questions?
No questions.
Okay, so we are done. See you tomorrow at 13 hours. Yes.